I am Anthony Antonetti.
I'm Lauren Sunder.
I'm Ryan Pagansky.
I'm Matthew Grant.
And we are NextStep Energy. So before we get into any of the testing data, we just want to go over our project objectives and the requirements we were trying to hit. Our project objectives, our main goal is to create a cost-effective floor tile that uses the direct piezoelectric effect to supply electrical energy for low-power devices. Some of our key goals are to generate electrical power from human footsteps, try to supplement conventional power sources, and while also keeping production costs low, to power small devices in public spaces, and to also promote renewable energy innovation. So our big overall statement is that we designed a floor tile that converts kinetic energy into electrical power.
Here are design requirements that shaped our project. We made the tile a box with 6-inch sides and 1.5 inches thick. The mechanical system required to actuate the piezoelectric elements, and electrically we had to harness and utilize that power.
Here are our mechanical components. This is from last semester. Last semester we had a slightly different design. We had a 10-sided shape inside a decagon. The idea was that we thought we could generate a little bit more power the more sides it had. But we took a lot of the constructive criticism from professors, and we also had to solve a couple issues ourselves, which brought us to this design. This design is an octagon. It has 8 sides in the middle, but only 6 of them have piezo connections, which I'll discuss soon. The top right is an image of the actual mechanical amplifier. This is our total design. The top wouldn't actually be off like that. The top plate is just removed so that you can see the inside of this. But this is our fleshed out design that helped to meet all of our needs. Our design only consists of 5 different components. Those components are, starting at the top row, the bottom plate. This is where everything sort of rests. The second piece is the mechanical shell. There are 2 of these. These are flipped, mirrored. This is what actually is part of the amplifier that compresses. After that is a clamp. That's our original design for a clamp. It's only the bottom half. That's also flipped on top of itself. The 4th image, first on the bottom row, is the longer clamp for extra support. And the final one is the top plate flipped upside down so you can see it's actually concave. This is the total amplifier itself. Like I said, the amplifying shells are 2 flipped on top of each other. When this gets compressed, this does 2 things. First, it slightly stretches out a piezoelectric material on the inside of the amplifier. When this piezo material is stretched out and then gets released from that tension, that is what generates a lot of the electrical charge. The other thing that this does is it meets the walls of the bottom plate around the edges. 6 out of the 8 walls that it meets have piezo material on those. When those get touched or compressed even slightly, those also generate some electrical charge. Here you can actually see where the piezo material would be. It would be on those 6 walls right there, minus the 2 that are way more concave. That's where our clamps go. You can also see in this design it has a hole there that is for our exiting wires. The entire idea of this is the vertical motion of that getting pressed down. This is exaggerated because it's very minuscule. Is transferred into horizontal movement, which stretches and compresses different pieces of piezo. As for the safety and stability of this, it only compresses a very minuscule amount. I think we measured 3 millimeters at most. So we're not concerned about anyone tripping, any safety hazards, anything like that. And the rest of the design was built with a lot of the other feedback from professors last semester in mind.
Okay, so now we're going to move into the piezoelectric effect and how we actually use that. So to quickly recap, the material that we're using is known as PVDF. It is a type of polymer, and that differs from what the commercial tiles use now, which is ceramics. We chose this because this is much more durable than the ceramic pieces. With any kind of material like this, they have coefficients related to its output. So here we have listed the D coefficient, which is related to the charge output. You can see that it has a direct effect on both voltage and current output. So what we tried to do was use area, force, and thickness to our advantage to try and get as much output as possible.
Here we have how we're using our system. So the person steps on the tile presses, the piezoelectric element deforms, and then an electrical pulse is generated AC, which is then rectified through a bridge rectifier into DC. The capacitor at the end of the circuit stores the energy, and then the cycle repeats for however many tiles that the person walking over, or if it's just the one tile, however many steps the person steps on it. Here is our circuit diagram. this is a purely representative piece because they don't have PVDF pieces in PSpice, so I just use a wire that's labeled PVDF. They are wired they are each rectified and wired to the rectifiers in parallel, which are then all come together at the end for the capacitor and our resistance, which we will go into more later why we chose that value.
All right, now we're going to look at the final prototype and some of our testing results. Here you can see the assembly step by step. On the very left is the lower plate with the 6 satellite piezo elements. In the middle, we have installed the mechanical amplifier, which contains the main piezo element, and then on the right, you can see it completely assembled. So here we have 2 videos up for you of it in operation. The left video is to show the voltage measurement on the oscilloscope, as you can see it pan over here. The spice is where you're seeing the AC voltage coming out. And then on the right video, this is just to show how little compression is actually seen. It's 3 millimeter, like Ryan said, so to avoid any trip hazards. So we encountered some roadblocks during construction. They range from the lab equipment issues to faulty assembly with soldering and placement of our components. We solved these issues. We had to end up ordering some new PVDF due to the laminator malfunction in the lab. And we also were able to use the new PDF for the satellite pieces that had the soldering errors.
Okay, so moving into the testing methods, after we did all of our preliminary testing with the material itself, we started testing the structure. So the first thing that we did was we ensured that the mechanical amplifier was acting as it should, which is providing more voltage output than without it. The second type of test we did was compare how the 6 satellite pieces in parallel would compare to the output of the main piece alone, and then how they compare all together. We also did complete the structure testing with both open circuit and short circuit conditions to try and get an idea of what our maximum output could potentially be. And then we also used varying forces with our 4 mega ohm resistive load and our capacitive load. So here you can see that the symbol itself does help amplify the overall output. So without the symbol, we were only getting 12.3 volts, and with the symbol we were getting 32.9. And then here is the comparison with the varying pieces. So our original design was to use the satellite pieces to try and increase the overall current output. However, with testing, we actually found that we limited the current output of the main piece itself. So per step, we were only getting about 2.4 microamps on average from a force of about 1891 ohms. And then here we wanted to include that with an open circuit and short circuit test, we were able to find that at 677 newtons, which is lower force than the previous slide, we were getting up to 123 volts and 36 microamps. So you can see that once you put your load in, there's going to be a very big drop in their output.
So here we have a varying forces graph. We asked a lot of people to walk over the tile to make sure that it was effective, was able to work at all different types of weights and sizes and stuff like that. So we started around 600 newtons, leading all the way up to 1100. It was really hard to keep people consistent when walking over it, but we did see that when you're actually taking full strides and you're walking over it, it did produce better results overall than just stepping in place. So our lowest output was 6.79 microwatts, our highest output was 5.233 milliwatts. Our average output across it all was 777 microwatts. Without the rectifiers, it was around 34. While walking, it was 643, and then walking without the rectifiers is 81 microwatts. Here we have the last part of the circuit, which is where it stores the energy inside of the capacitor. As you can see, when we start the graph, each pulse where it goes up is someone stepping on it. It is in parallel with the 4 mega ohm resistor. We completed this test with 890.9 newtons because that is kind of like around the average weight of a U.S. citizen. Each peak occurs with the footsteps, as I said before, and the faster someone walks on it, the more it charges. Here we have the budget. So on the left, you can see this is what we spent. Because we had to buy the extra piece of piezo material. It brought our budget up to $484.94. And then for a real world scenario where there's no extra parts being bought, it would cost around $384.89. Here I did some ROI and projections if there was more multiple tiles in a system. I would go into a lot of detail, but I think the overall point is that if we look at the ROI, each scenario is negative 100%, meaning under extreme pedestrian conditions that I found to be around 20,000 steps per day, piezoelectric harvesting remains a micro power system. It can't overcome the cost or energy density limitations as right now, or at least our system.
Okay, so moving into conclusion. So we do have some positive findings, such that we were able to output measurable voltage and measurable current. We were also able to ensure that the amplifier was doing as we expected it to, with getting much more output than if we didn't use it. And we were also able to lower the cost of the overall tile to be less than what is commercially available. The negative findings, however, is that we weren't able to get enough power to actually be usable with just one tile. The outer material itself ended up being limited by the main piece of material ended up being limited by the outer pieces of material, which was not what we were expecting going into this. And then the last thing was that we weren't able to power an LED or turn it on because the power was so low using our circuit that we have this time. Looking forward, of course, this design can be improved overall, hopefully to get more power outputs that you can see, or have some kind of visual that there is power output. And then, of course, we would hope this project acts as a starting point for more renewable energy projects.
We've got some acknowledgements. We'd like to thank Dr. Khan, our project advisor, for all of his help, along with Dr. Bednarz for teaching the class. We'd also like to thank Terry Chase for giving us a lot of different opportunities to present and see the business side of everything. And of course, we'd like to thank Mitch for all of his hard work in the machine shop. And finally, we'd like to thank Suzanne Stash for putting this all together, along with all of the engineering students who helped us get our data. So thank you to everyone as is moving here today.
Good job, team. I'm going to let other professors comment on the electrical side. I'm going to go to electrical heavy design, but I do have a question for the mechanical portion. Can you go back to your testing data where you had the force versus your output? So is that force just the person's weight?
That force is literally just the person's weight multiplied by the mass times acceleration. So
it doesn't take into account the impact. If someone's gently stepping on it versus vigorously stepping.
We were trying to get people to just put all of their weight, depending on what we wanted them to do. That was kind of like the only thing we were telling people to do.
So I guess my question then is how, and you don't have the testing data for it, but from a theoretical aspect, how would that affect if someone was just walking gingerly along, or if they were vigorously running on it? Would you get more power?
You would get more power. There's technically supposed to be a linear relationship between voltage and force. It goes up as force increases. So if someone were to run on it, they would be exerting more force on it, which would in turn produce more voltage. Or if you were jumping on it, it would produce more voltage, depending on how high you jump and stuff like that.
Yeah, we try to do some tests with that, stomping on it versus just walking across it. Ideally, this would be in a scenario where there are many tiles, dozens, maybe 100 tiles in a pathway, because that would be a lot more consistent of walking, whereas now we have to step up onto it a little bit since it is raised up above the ground as just one tile. So it was a little tricky to test with that since we couldn't afford to make multiple tiles, but we did try to account for that.
Yeah, so when you're saying it's not a tripping hazard, they would all just be in the same
Yeah, it would
level.
be flush with the ground. They would be in the ground, yeah.
Okay, any other questions?
You go that way first and see if it gets answered. I'm warming up this.
So I have a couple of questions. So first question is, how do you choose a piezoelectric material for your project?
For our project, we had to choose between durability and reliability and other factors like that. So there's more than one type of piezoelectric material. There's the polymer, which is what we chose, which is a lot more durable and flexible. There's also a different type known as a ceramic, which would create more power. But the thing about it is that it's super brittle, so it could break easier than the polymer.
So what are the material parameters you look at? Like what should be the like piezoelectric charge constant, or which parameter you look at? When
We're
you-
looking at the charge constants and the stress that it can take and other factors like that.
So in the project, I mean, I was looking for like you mentioned you are gonna make these tiles. So did you predict how much power you are expecting from these tiles and how much you are getting? Do you have this simulation versus experimental comparison?
We do, but for the presentation, we had a lot of data to present, so we thought that it would be more important to present our raw outputs rather than the simulations of what could potentially happen.
Did you have any target like power? You are gonna produce this power that you have calculated?
We wanted to produce enough power to power an LED, but we weren't able to hit that goal, but we were able to make a working circuit.
So another thing is like you mentioned about mechanical amplification, right? So what's the amplification factor here? How much you are amplifying the force?
We're unsure exactly how much it is amplifying the force. We weren't entirely sure how to get a good measurement of that because we're limited by a few factors. You see, on the inside of the tile, it's only able to stretch so far before it will hit the walls. So we're not exactly sure that is something that we should have tested. And if we were to go forward with this, that is something that I would look into.
Okay, and one last question. Are you the first making this, or are there any similar projects? If so, like, what's the difference that you are doing here?
Our difference is that ours is a lot more cost efficient than others are in terms of actually making it. It's a lot
Other than
cheaper.
cost, I mean, other than cost.
Definitely the two different ways we're trying to generate energy. A lot of other tiles only generate energy one way, like with the stretching or the compression. We tried to do both in one tile to see how it would affect it.
Plus, with the mechanical side of it, this is actually a popular method of energy gathering in Japan. I mentioned that in last semester's presentation, and their tiles can use upwards of dozens, tens, many more pieces. Ours, when designing it, we try to keep it as simplistic as possible. Therefore, if something were to break or get damaged, it's easily replaceable. If someone wanted to try to make this themselves, as we can see here, it is not too difficult to make because of how simple the design itself is. So, aside from cost, there were a couple other things that were influencing the decision.
One last question. So, apart from the piezoelectric effect, do you think what other renewable technologies would be more suitable to design this project, or that's the best you think?
Could you repeat the first part?
So, other than the piezoelectric technologies, do you think are there any technologies available that would be producing more output power than the piezoelectric effect is giving?
It's possible. We didn't really look into too many other methods. Maybe we should have, but we really wanted to focus on taking this pre-existing method and making it the best that we could with our own skills. But yeah, we could have looked into other methods as well. Thank you.
I hate to ask a question and whatnot, but so just to double check, the tile itself compresses from the top, and then the symbol is able to stretch the piezo material and whatnot to generate power. So the piezo material, does the tension on it displace it much? As in does it how much does it stretch out, or is it just completely negligible?
We didn't have to worry about how much it's stressing out based off the simulations that we've done last semester. And then this semester, because the symbol, you can't really see how far it stretches outward. It's also not stretching the material enough. We've done multiple testing, so even if we can't get a direct measurement, we know that with all the repetitive force, there hasn't been any damage to the material.
Okay, because I was just concerned about the material getting damaged, because I remember you presented the graphics of 20,000 steps a day
Yeah.
for average pedestrian traffic. I was just concerned about the piece of material being damaged and possibly having to replace it to be able to stretch and pull it too much.
And that's exactly why
go back to that you said earlier. This one. How did you choose that 4 mega ohm load as an optimum?
We did something called resistor matching. Basically, the way we did it was we started at 1 mega ohm to try to match the internal resistance of the piezo because it has a high impedance on the inside. So we started at 1 mega ohm, brought up the 2, and then tested until we saw basically a graph where it was producing more at 4 mega ohms than any of the other resistances that we were checking.
Can you go to the slide where it shows the power generation within the chart? I want to see what's close. No. That's next. Can you explain why all your power, like all your pieces, your total output power is less than what you get with only one piece? Because if you rectify main piece, it generates 68 microwatts, but all pieces only generates 23 microwatts.
So we have a feeling that it's because of the design of the structure itself. Within the structure, if all material is being activated at the same time with that main piece of material, I think that's where we would have seen the additive current, but we didn't see that because not all the material is being activated as it should. If there's any kind of lower charge on that one material, so the smaller piece, it's going to pull some of that charge from the main piece to that little piece, and you'll get less output.
Run, Ed. Come on.
I know. Getting old.
So, quick Google search found 3 different ways of doing this. You know, the one question that you had is, did you look at any other ways? So it would have been worthwhile to look at, besides piezoelectric, you could have done electromagnetics, and there's a couple of other ways. So you could have looked at that. A trade study would have been nice. Okay? It wasn't a question, it was just a statement. But where would you see this being applied? Because I can't see this being applied at a home, so I can't see somebody doing it at home. Where would you take this and apply this? And how many tiles would you need to generate the power that you're looking at?
So ideally, these tiles, if you have them in a system, there would be like hundreds of these tiles all together. Right now, where they're being used the most is in where there's a lot of people walking. So any kind of like transportation systems, any kind of busy cities, that's where you'll find it. I think it's most popular right now overseas. Right, with our tile design though, because the output is so small, this would need to be optimized much more to actually see the outputs that you can get overseas with their tile designs.
Okay, yeah, so that's what I had seen is mostly overseas, but you know, airports, bus terminals, things like
I
that.
think a lot of people, that's where you want it.
Okay, thank you.
One last question. Last one.
So how did you calculate the power?
So what we did was we tried having people step or walk across the
Like
tile.
what equation did you use to calculate the power?
We measured the current on that resistive load, so then we took that current, squared it, and multiplied it by the resistance to get the power there, or the power output that you would expect. And then as for how we actually measured it, what we did was we had them step across it, so that we would have them try to be as consistent as possible based off the oscilloscope, and then take what those peak values would be and use that value.
So if you think about this is in a micro. I mean, anytime when you talk about the power generation, if it's a micro, I've never seen, and I've heard that, I've never seen microwatts as a unit. You see what I mean? That's basically, I mean, I was doing a quick Google search. Your body radiation is 100 watts. You're talking about, I mean, if you can put 1,000 there, that's how many? That's mini. I mean, that's not even going to light up an LED or anything. So is this actually feasible? Is this actually?
I think right now there would be a lot more research that needs to go into the materials being used because we're still limited by the coefficients involved with the material itself. So admittedly, we chose a material that's already going to have a lower output versus a ceramic material. But even then, like you said, it's not high enough where it would be feasible to replace anything at all. It would be better suited for more
because piezo are not cheap. You're talking about thousands of them to generate something to light up LED, and that doesn't make financial sense.
Yeah, so the goal was to do some kind of research into renewable energy to really try to highlight that, try and shift away a little bit from fossil fuels. But again, a lot more research needs to be done into this type of project to actually make it a feasible project.
So I circle back to the one Dr. Khan was asking, which is for this kind of project, I mean, I guess my main question is this results actually a surprise to the entire team? Is this something you would expect? I mean, is this a surprise?
I would say we were still expecting somewhere in the microwatts. We were hoping something would be higher than the average of 23.1 microwatts that we're getting. We were hoping to be in like the hundreds at the very least. But that could also be due to the mechanical design. If it's not fitted properly and all the pieces aren't getting activated at the same time, there will be a limiting factor there.
But even if like hundreds of microwatts, that's still no go from a project perspective. You see my point here? Because if you know, you have to kind of, a little bit of theoretical background research, you know you are not getting any power out of this. So that's, from a project at the beginning, on planning perspective, you get to know what you're getting into. That's just, a little bit of research will help on that. So, thank you.
Okay, thank you.